Swayam Prabha. Digital India. Educated India.
Hello everyone. So, we are discussing the protective textiles for gases and chemicals, hazardous gas and chemicals. Now, coated and laminated barriers materials. So, these are basically elastomeric coating which transforms the base fabric into a impermeable barrier against the liquid chemicals and gases. So, this type of coatings are neoprene coating, maybe butyl rubber coating, fluoroelastomeric coating. So, this fluoroelastomeric coating is outstanding resistance to aromatic hydrocarbons and chlorinated solvents. So, different types of elastomeric coatings are there. And nitrile rubbers are used, EPDM rubbers are also used for the coating. Then high performance synthetic materials are used, these are engineered polymer for high performance high protection scenario, okay, maintaining the wearer's comfort and durability, that is important. Like polyesters are still used for this gas and chemical protection. These are durable base fabric with excellent dimensional stability and some chemical resistivity is also there. Polypropylene, it is a low weight, polyethylene films are used, PU coated fabrics are used for gas and chemical protection, silicon coated fabrics, okay. The PU coated is basically for chemical splash protection, silicon coated fabric high temperature stability with flexibility, and it is a specialized heat and chemical application. So, the technologies are, we can use that electrospun nanotechnology, nanofiber we can use. So, ultra fine fibers membrane with submicron pore size, okay, that we can use, which will actually be used for chemical protection, but which will at the same time it will maintain the breathability, moisture vapor transmission will be there. Then graphene oxide compounds can be used. MXN textiles. So, that is two dimensional transition metal carbide which offers the electromagnetic shielding. Now, smart and adaptive barrier systems, smart polymer barriers are used, phase change compatible fibers. So, the critical fiber level performance properties are its permeability behavior. So, breakthrough time, permeation rate or degradation resistance, okay. These are very important for any fiber to be used for chemical protection. The breakthrough time should be high, permeation time should be less and it should be degradation resistant. So, that is very important. Next is comfort and ergonomic. So, the fiber or fabric should provide the breathability, flexibility. Okay. It should be chemically resistant. Okay. It should not react with the hazardous chemical. The fiber should be mechanically stable. So, high strength abrasion resistance should be there and it should be heat resistant. So, thermal degradation should be should not be there, okay, and it should be flame resistant. That means this fiber should be thermally stable at high temperature. The material selection, actually the effective PP design requires balancing of comfort, durability and cost. So, understanding the fiber properties enable optimized solution for the specific hazard scenarios. Like we have to identify the type of hazard. So, what is the classes of chemical, what is the concentration, what will be the exposure duration, then only we can select our material. And we have to test or review the resistance data. Okay. Like consult the permeation chart or compatibility matrices, that we have to review and then select the application. So, we have to evaluate the performance, both mechanical, heat resistance and comfort factor. So, we have to evaluate all this performance, because we are selecting proper material polymer for the chemical protection, but all the mechanical, heat resistance and comfort performance should be there, and then we have to select and then validate by proper testing. Now, the fabric structures for chemical and gas protection. So, advanced textile engineering is required. So, understanding the fabric structure is essential for protecting against any chemical and gas hazard. So, nonwoven technology is widely used. So, there are different manufacturing methods, we are not going to discuss here in detail, like spun bonded, melt blown, SMA structure, spun bonded, melt blown spun bond structure, multi-layer structure to provide the mechanical strength and barrier properties. Microporous membranes are also used to, like in a membrane we can create micropores which will allow the moisture vapor to be released, but prevent any chemical or gas from permeate from enter through this type of barrier. So, pore size engineering is required. So, typical pore size is 0.2 to 10 micron. So, these are small enough to block liquid chemical, but allowing the vapor to escape. Common material is EPTFE, expanded polyurethane and polyurethane film. So, that is used, or normal polyethylene also we can use. So, application range ideal for type 3 and type 4 suits. So, monolithic membranes, so which are impermeable membranes in some cases where the activity duration of activity is very low, very that is a low small time. So, in that case and for very threat is very severe, in that case impermeable membrane we can use. Unlike microporous membranes, monolithic membranes contain no pores. So, protection relies on the molecular diffusion through the solid polymer film. So, this characteristics polyurethane or PVC coating provides continuous barrier, and hydrophilic polymer transports moisture via absorption and desorption. Superior resistance to chemical that wet micropores, high heat stress due to the reduced breathability, laminated composite we can use for improved performance, we can engineer the performance. So, the substrate layer like base layer is oven or non-oven for structural strength, and barrier layer. So, microporous or monolithic membrane are used to block the chemicals, and also after that we can use the protective outer layer to protect from the abrasion, okay, and also protect from any physical damage, chemical splash or environmental degradation. So, protective outer layer is also used. So, 3 layer structure: substrate layer, barrier layer and protective outer layer. So, adhesive or thermal bonding techniques are used, must preserve barrier integrity. So, these 3 layers should be integrated. So, adhesive or thermal bonding technique can be used to make this all these layers intact. So, multi-layer barrier system, you can see advanced PP combines multiple specialized layer with a strategic architecture to maximize the safeguard. So, outer shell which is durable, chemical resistant surface and which provides abrasion resistance, and it comes under the initial contact of chemical. So, it should be chemical resistant. Then barrier layer which actually prevent the chemical or gas penetration, and comfort layer, inner layer is comfort layer which will absorb moisture, okay, and tactile comfort will be improved, senses it should be soft, and optional adsorptions are there. So, activated carbon we can add to have better protection, chemical neutralization capacity. So, activated carbon and nanofiber we can incorporate. Activated carbon fabrics, the carbon particle embedded in or bonded to the textile substrate. So, it is embedded within the carbon particles are embedded or it is bonded to the textile substrate for absorbing the organic vapor. So, carbon particles are activated, carbon particles are embedded. So, microporous carbon structure traps the molecules through the physical and chemical adsorption. So, this activated carbon fabrics are effective for volatile chemicals. Okay. And nanofiber layers are also used on the substrate, and diameter typically 50 to 500 nanometer diameter, creates ultra fine filtration barrier, which prevents the from that chemical to enter penetrate. Superior particle and aerosol filtration, that is any gas, toxic gas protective textiles, we can use nanofiber layer, maintain low vapor pressure, so that breathability is maintained. So, it is for next generation PPE, this type of carbon nanofibers layers are used, activated carbon nanofiber, and these are any nanofiber layer we can use here. So, film coated fabrics, particle protection. So, polyethylene film we can coat, which will be low cost coating, provides basic liquid splash protection. So, the polyethylene film can be coated. PVC or nitrile coating we can use, superior chemical resistant to acid, base or solvent. So, nitrile coatings are used, but it is heavier or less breathable because of the nitrile coating. And fluoropolymer coatings, exceptional resistance to aggressive chemicals and high temperature. So, for very excessive aggressive chemicals we can use the fluoropolymer film. So, impermeable versus permeable suits. So, impermeable basically gas tight, so that there will not be any permeation through this material. So, type 1A, 1B suits, fully encapsulated system, there is no breathability, permeability, totally impermeable. So, which is by butyl rubber, Vitron and laminated film is used, where the breathability is 0. Okay. Maximum protection from unknown or highly toxic agent. So, where there is a we need to have protection from unknown gases or very toxic gases, in those cases we can use the impermeable gas tight material, it is labeled as type 1A or 1B suits. So, problem here is that severe heat stress and which limits the work duration, when someone has to perform for a very short duration at extremely toxic gases, in that those applications we can use type A, 1A or 1B suit, and there will be permeable type of suit, which are type 3 to type 6 suit, which actually are used which will permeate the air, but it will be splash and particle protection will be there. So, microporous structure, so moderate breathability will be there, and it is not suited for the gas or vapor exposure. So, for toxic gas exposure, this type of permeable PP is not suitable. This is mainly for suitable for splash or particle protection, most common for industrial chemical handling. Critical design factors are there. So, breathability trade off is 50%. So, we can depending on the threat level breathability we have to compromise. Then critical pore size is typically 10 micron. So, maximum pore diameter for liquid barrier with by maintaining the vapor permeability. Then optimal layer 3 to 7 layers we can use. Critical design factors are design considerations, layer by layer architecture we can use. So, layer by layer allows the engineers to optimize each function independently. So, we can use different layer multi-layer which will actually perform each layer will perform its independent function. So, real world case studies, this real world case studies demonstrate successful implementers, that is SMS nonwoven for healthcare PPE. So, like spun bonded, melt blown and spun bonded. So, multi-layered structure. And also activated carbon layer also used, that is for chemical, biological, radiological or and nuclear defense. So, different types of protective textiles are used for protective barriers are used multi-layer. So, material selection depends on threat assessment, exposure duration and environmental condition. So, this for before any designing any critical PPE. So, threat assessment has to be there, what will be the exposure duration and what type of chemical environment with gas, if it is gaseous gas pollution and that will be which gas. So, what type of chemical, if it is chemical what type of chemical, that condition, these conditions we have to understand clearly. So, the barrier mechanisms against chemical and gases. So, this barrier mechanism we have to understand in detail. So, this fundamental science we must understand. So, how the protective materials defend against hazardous chemicals. So, in the industrial and emergency response environment. So, this type of hazardous chemicals are we have to actually protect ourselves from these chemicals and gases. So, core mechanism is that first is physical blocking. So, there has to be physical blocking from the this type of chemicals. So, dense molecular structure prevents passing of chemical molecules through the mechanical structure. Okay. Then sorption process, chemical absorption and desorption within the barrier matrix, that is that chemical neutralization. So, active chemical reaction which converts the hazardous chemical into a normal chemical, it is basically which be inactive chemical will be there. And molecular sieving, size selective filtration allows the small molecules with blocking range chemical structure. Okay. So, blocking the large chemical structure. So, we have to actually that chemical molecular sieving has to be there. So, large chemicals structure will be blocked. So, this type of physical blocking, sorption process, chemical neutralization and molecular sieving, these are very important characteristics mechanisms. So, we must adopt for designing this the chemical and gas protective textiles. So, molecular interaction principles, like hydrophobic barriers has to be there. So, water repellent materials such as certain rubbers, fluoropolymers that resist the aqueous chemical solution. So, that hydrophobic barrier has to be created. So, the PTFE, that polymer silicon based compound. So, this we can use hydrocarbon elastomers we can use. One is hydrophilic barrier, another is the hydrophobic barriers. So, hydrophobic barriers actually, so polar materials like PVA or certain polyurethane which attract and interact with the water molecules, creating effective barrier against non-polar solvents. So, this type of reactions has to be there, okay, which will interact with the water molecule and ultimately create a barrier against a non-polar solvent. So, that type of after reaction this will create a non-polar barrier. So, PVA, polyvinyl alcohol is used, hydrogel structures, so modified cellulosic material. So, this interaction, molecular interaction with the chemical or gas, hazardous chemical or gases is done by hydrophobic barriers and also by hydrophilic barrier. In hydrophilic barrier, it absorbs water, but it is used to create a effective barrier, and in hydrophobic barrier that it does not allow the aqueous liquid chemical to penetrate. So, diffusion resistance and polymer architecture, cross linking is one way of doing that. Then by changing the polymer density. So, higher molecular packing density increases the barrier effectiveness through reduced free volume. Then third is diffusion control. So, this cross linking is one way, polymer density can be manipulated, and diffusion control by restricting the molecular mobility within the matrix, slow chemical migration through the barrier. So, that we can target. The degree of cross linking directly impact both chemical resistance and mechanical properties. So, we can control the cross linking. Higher cross linking material exhibits superior barrier, okay, with the which may sacrifice the flexibility. So, if we increase the cross linking, it will increase the barrier performance, but flexibility may be it may be rigid. So, advanced protective coatings are zinc oxide coating, okay, which neutralizes the acid and organic compounds. So, zinc oxide, so which coat and any chemicals, organic compounds or acid, if it comes, it will neutralize and its effective corrosive effect will be reduced. Then titanium dioxide, which breaks down the organic chemicals upon UV exposure, okay, provides self cleaning surface with enhanced chemical degradation capability for long term protection. Then amine based treatments are also used for advanced protective clothing. Then carbon adsorption, it is actually due to the activated carbon provides exceptional protection through extraordinarily high surface area. In 1 gram it provides 3000 square meter surface area and it creates millions of adsorption sites. The key steps are chemical vapor contact, it contacts carbon surface, van der Waals force attract the molecule, then molecules adhere to the pore wall, pores become saturated over time, and the main limitation is that activated carbon has a limited capability and requires replacement when breakthrough occurs. So, after absorption, so it has to be replaced. So, that is the main limitation, we have to replace the carbon activated carbon layer. And material thickness and permeation dynamics. So, if we increase the thickness by 2 times, doubling the material thickness can increase the breakthrough time by 4 times. So, that is important for any emergency situation where we need to increase the breakthrough time. There we can do it by increasing the thickness of the textile material. So, optimal range is the typical protective gloves thickness typically from 3 to 5 millimeter. And permeation time is actually standard test duration is 60 minutes. So, we test the permeation for 60 minutes. So, permeation time increases the proportionality to the square of the thickness. That is, if we increase the thickness by 2 times, permeation time will be 2 square, that is 4. If we increase by 3 times, it will the permeation time will increase by 9 times. So, square of thickness, but excessive thickness will enhance the will reduce the tactile sensitivity, it will be very bulky and the stiffer structure will be there. So, critical performance calculations. So, breakthrough time, which represents the chemical penetration, reaches 1 microgram per square centimeter per minute. on the other side, other surface. So, that much chemical if it penetrates, and how, what is the time, that is the critical safety threshold, that is breakthrough time. And how is it determined? So, permeation rate formula is that d S delta C, where d is the diffusion coefficient, S is the solubility, delta C is the concentration gradient, and L is the thickness of the material. And breakthrough time calculation, this is L square by 6 d, that we have discussed. The breakthrough time is proportional to the square of the thickness. If we keep the, for the same diffusion rate, if we increase the thickness by 2 times, so breakthrough time will increase by 4 times. And safety factor application, so it is basically safety factor minimum 2 times safety factor is used to calculate the breakthrough time. Environmental stress factors during the extreme gas and chemical protection, swell resistance. So, chemical exposure cause polymer swell, we have to see that it should be resistant to swelling. Thermal influence. So, every 10 degree increase in temperature roughly double the permeation depth, that is important. So, as we increase the thickness, the permeation rate reduces, but if every 10 degree increase in temperature, the permeation rate becomes double. So, we have to design the text material for different temperature. The high temperature accelerates the molecular diffusion and reduce the breakthrough time significantly. And pH effect. So, extreme pH condition hydrolyze the polymers and degrades the barrier integrity. So, material selection must account for acid or alkaline exposure. So, for environmental case like swell, it should be swell resistant. So, in case of when the chemical comes into contact of the polymer, it should not swell, okay. And the thermal at different temperature, the permeation rate changes, and we have to see the chemical what type of what is the pH level. So, that this degrade the material, and critical consideration is that standard laboratory test 23 degree Celsius ambient condition may not reflect the actual performance. So, in testing standard test condition, we perform the test at 23 degree Celsius, but if we get the certain permeation time, but if we in actual condition, if it is say 60 degree, at that temperature the permeation time will be changed, permeation rate will be very high. So, in real life situation, we should predict the what will be the permeation rate or different other parameters. So, always we should account for the worst case environmental factors. So, what will be the temperature, what will be the pH of that condition, accordingly we should design our protective textiles. So, real world failure modes are physical damage will be there. So, there will may be puncture, maybe tear, maybe abrasion, and if there is a tear, then the there will be easy penetration of chemical and gases. So, we should test, we should be ready for this real world failure modes. So, physical damage should maybe that it may get degraded due to UV exposure or heat exposure. Okay. And contamination transformation may be that it may be contamination can get transferred to the skin from the exterior to the skin. Saturation breakthrough, seam and interface failure. So, the protective textiles are there, but there may be failure in seam or joint, or there may be opening between the seam. So, this real world failure modes we have to consider. The key takeaway here, this understanding the barrier mechanism enables informed PPE selection, proper usage protocols and realistic expectation. So, we cannot expect very high in real world situation by depending on the laboratory scale test data. So, that we have to take care. So, that for that regular inspection of the PPE, appropriate material selection is required and adhere to breakthrough time limit are essential for worker safety. So, there are some innovations in functional finishes and coating. So, exploring cutting edge surface treatment are there like fluorocarbon finish or oleophobic finish, that oleophobic coatings like superior repellency is there. So, if we use the fluorocarbon finishes, okay, so we will get the superior chemical repellency. It delivers exceptional oil, water and chemical resistance. Like environmental progress, recent innovations focus on reducing or elimination of PFAS like different types of substrate. So, that like plasma and sol gel coating. So, precise surface engineering is required. So, by using the plasma coating or sol gel coating, by plasma treatment the activates the surface at the molecular level for enhanced adhesion and functional layering capability. So, first we should treat the with the plasma treatment, then sol gel treatment creates ultra thin durable film, okay, including UV protection and scratch resistance. So, this also used the sol gel technology is also used for gas and chemical protection. So, for industrial applications, that is critical for automotive, aerospace, medical devices, and super hydrophobic and self cleaning surface. So, lotus leaf mimicry. So, we can create the super hydrophobic surface which will actually repel the water based chemicals and prevent the contamination and corrosion. On the textile surface we can create this type of super hydrophobic coating we can do, we can that surface we can create, and sustainability benefits are that it reduce the cleaning requirements. So, cost of maintenance is reduced, and we can save water, enhance functionality, like we can use the TiO2 nanoparticles, adds antimicrobial activity and also pollutant degrading capability. So, pollutant also degrades the textile material. So, that capability we can also reduce. So, chemical resistant polymer and organosilicon coating. So, we can use different chemical resistant polymers. So, for industrial protection, and advanced polymer coating provides robust defense against the harsh chemical industry, medical and laboratory environment. So, organosilicon formulations offer exceptional thermal stability. So, this we use on the chemical resistant fiber, like flexible molecular structure maintains integrity under the extreme condition, critical for aerospace components and protective clothing system. These coatings extend equipment lifespan with, while it ensures the worker safety in demanding exposure. So, for like chemical and gas exposure, so we can use this type of organosilicon coating. Nano coatings are also used, okay, animated reactive finishes. So, nanoscale engineering is important for protecting against the gas, the toxic gas and chemicals. It provides barrier properties, electrical conductivity and enhance the mechanical strength at molecular dimensions. Covalent bonding is also, we can that, and smart applications. So, antimicrobial or UV stability finish we can also give with the to the these protective textiles. So, silver nanoparticle or chitosan, okay, this type of finish for long term use. UV stabilizer. So, people may get exposed to the UV ray, and along with this protection we need UV stabilizer for outdoor applications. So, fire retardant synergy and compatibility challenges, it is very important, because in case of any fire, along with the fire there will be toxic gases or even the chemical spills will be there. So, what do you do? We have to use the chemical protective textile, we have to use the gas protective textile along with the fire protective. So, there should be a compatibility. So, that synergy should be there. So, innovative synergy is that we have to use a multi-component system to create superior protection while maintaining the breathability and flexibility. Multi-component system like for fire protection, for chemical protection or for gaseous protection, that we have to take care. So, R&D challenge, we have to balance all these requirements. The road ahead is the durable, sustainable and smart coatings are the main requirements. So, AI driven innovations are important. So, predictive maintenance algorithm and self healing. So, that self healing materials are required, sustainable solution. So, bio based eco friendly coatings are important. Actually, to have the environmental to achieve the environmental responsibility goal. So, industry transformation. So, combining protection, performance and sustainability to reduce the manufacturing standard, to redefine the manufacturing standard, because we have to redefine, because our manufacturing standard is not to have high production or best quality product, but at the same time there should be a sustainability. So, that basically we have to redefine our standard, we have to incorporate the sustainability within our production. So, functional finishes are no longer just protective layers, they are intelligent adaptive system that enhance the performance while honoring our commitment to the planet. So, smart and advanced protective textiles. So, exploring the cutting edge innovations, transforming the personal protective equipment through intelligent fabric and embedded sensor system. In any protective textiles, particularly this fire protective or extreme chemical protective or gas protection, we need to understand the presence of the hazardous chemical or hazardous gas, we have to monitor. So, that for that we need a smart textile. So, embedded sensors in chemical protective suits, that is the future requirement, where we can have real time detection of presence of particular type of chemical. So, there is a textile integrated metal oxide framework to detect the chemical penetration in real time and alert the wearer instantly to hazardous leak. So, the wearer, those who are working in front of any hazardous chemical, and there will be a metal oxide framework embedded on their protective textiles, and which will alert the wearer immediately. This fabrics actually this fabric combination actually sense, capture and filter the toxic gas like nitric oxide, hydrogen sulfide, this type of toxic gas they first sense, then capture and then filter. Similarly, gas detection textiles, we can sense the presence of particular type of gas. That is flexible monitoring system. The porous sensors continuously monitor the ambient gas for toxic gas presence. So, the sensor will be there which is embedded with the protective textiles, and it will continuously monitor the ambient gas. Okay. In case of any toxic gas is there, it will immediately sense. Even the monitors are there, it will be able to sense the what type of gases are there. Then it will actually connected to the network, the real time hazard alert will be there and transmitted through communication system. So, this gas detection textiles are important for protection and giving alert to the wearer. So, critical protection essential for emergency response and military personnel in hostile environments. Also, there are color change hazard indicator. So, in presence of different types of toxic gases or chemicals, the protective textile with color change indicator will change its color depending on the type of chemicals or gases. It will react with the this component present in gas or the chemical and it will change its color. So, visual it will give the visual warning, like this is a normal here. In when it comes into contact with certain chemicals or gas, it will change its color and that will give someone a visual warning of presence of the hazardous gas. So, halochromic textiles are there which use the pH sensitive dye. So, if in case of chemical, so there will be pH sensitive dyes will be there that visibly change the color upon in contact with the acidic or alkaline. If even if it is coming under the in contact with acidic chemical or alkaline chemical, and as the dye is pH sensitive, it will change the color, okay, provide instant visual feedback to the wearer. So, that wearer can know that okay, there is presence of any toxic chemicals, hazardous chemicals are there. In the recent advancement, so which allows industrial scale stamping of these sensors on polyester fabrics. So, we do not need to color all the material because of the it is a costly material. So, in a normal fabric say polyester fabric, we can stamp with this type of pH sensitive color this pH sensitive dyes, and that portion there will be that will sense as the any change in pH. So, industrial scale stamping these sensors or polyester on polyester fabric provide immediate visual warning of chemical exposure. So, if we can print with some portion or stamp in some portion with this type of pH sensitive dye, okay, then it will give the immediate immediate warning of presence of any chemicals. Okay. So, the future of intelligent hazmat suits that this we will discuss in the next session. Till then, thank you.